that line. That'll get us going. Thanks everyone for joining. It is 3 minutes past the hour, so we'll roll into this stuff. This is Energy Modeling for KP Projects. My name is Travis. If you are looking for AIA credits for this, Melanie Kramer is our contact for that. Her email address is on the screen. Go ahead and ask her for your AIA credits. Also, during the presentation, if you have questions, go ahead and type them into the WebEx chat box and send those to Melanie. And then we should have a good amount of time here at the end of this presentation. Here's our agenda. I'm going to scroll through this relatively quickly. But yeah, we should have, this should take, you know, about 30 minutes of talking at you. Sorry for that. And then we should have a good amount of time afterwards. I've seen some of the names on the list, so I know there's a couple of you that I know personally. For those of you who are lucky enough to not have run into me, my name is Travis English. I'm with our National Standards Group at Kaiser. And I do have a pretty cool job. In my department, we very often find ourselves right up at the edge or slightly over the edge of the things that we take for granted in the design community. So I get to spend a good amount of time in the 20% of the 80-20 rule. I try to keep that in perspective. The vast majority of what our design partners do for us goes swimmingly well, and we never hear about it. Today we're going to be talking about energy modeling, which is an area that is in that 20% that we need to do some adjusting here. I do want to thank everyone who gave us commentary on the last round of our life cycle cost white paper. I know we had some good email discussions. Thanks for your feedback on that. You'll notice it's not published yet. You should expect to see that in Q1 of 17. And so to get this story started, I want to tell you a little bit of my story. I came to Kaiser in 2011, and at that time we had no energy modeling requirements for our projects, and particularly our new designs. Most of our medical office building projects were doing it anyway, because in California we have California Title 24, and so some design firms were using the same software to do their load calculations. Some design firms sort of run two sets of calcs. But as the owner on our side, we really weren't paying attention to that. We weren't looking at them. And so that's where we started. We said, hey, look, most designs are doing energy models anyway for Title 24 purposes, so let's start looking at them. And we did. That's how we got in the energy model review business. And after a very short time, we made that a company standard. We added project requirements to A, do energy models, and B, to hit certain targets with the design energy models. We put out a white paper in 2012 showing the numbers that we expected to see in the design models. And I will put emphasis on the word design right there. Now, right about that time, we had a project that was in design, pretty progressive project, the Antelope Valley Medical Office Building, where they were going after sustainability in a pretty big way. LEED was not yet a Kaiser requirement, but they were blazing that trail. And the project was a something million dollar project. And we went and submitted a business case that said this project's going after sustainability. It's going to save energy and water. And we requested an additional $8 or $9 million and said that it would pay back in about 5 years. And that business case went through very well, and we got the money. So flash forward, this bottom corner, bottom left corner, what you see here, CA2601 Antelope Valley MOB, that's that project. So you see the modeled energy is that red line, and then the actual energy is the blue line. And you look at that and sort of say, oops, right? Now the story isn't really quite that bad. To put this in perspective, the modeled energy, for those of you who speak in terms of EUI, energy use index or energy use intensity, the modeled energy of that building was about 40 EUI. Our Kaiser average MOB in Southern California was about 100 EUI or 110. It came in at about 60. So relative to the portfolio, the building is doing quite well. But relative to the energy model, not so much. And on that project, we actually did what the USGBC says to do. We went in and did a 1-year post-occupancy calibration of the energy model like the IPVMP protocol says. And we'll say more about that later, but those are the results, right? some of you were at our preferred provider forums and you saw these charts. We have a whole set of these charts. And generally what we're finding is that the actual use is significantly higher than what we see in the design models. And that's really what we're here to talk about today. So in the U.S. new construction marketplace, the standard practice is to use energy models for comparison purposes, and mostly in a compliance context. We have kind of two major standards, California Title 24 and ASHRAE 90.1, and during designs, teams run the models to meet those standards. You might be doing that to comply with code, as in the case of California, or to comply with the standard for LEED purposes. But in any case, it really isn't a budget prediction, it's a compliance model. That's what's common in U.S. new construction. Now in the UK, in Canada, in Australia, and some of the other English-speaking Southern Hemisphere world, energy models are used in the much more practical context. They actually predict utility costs. UK and Canadian health markets, they use this so-called triple P delivery method, where the designer and the builder and the operator work together and guarantee the owner a lease rate. And we have seen that in some U.S. government or university work. And so the energy models done by those designers are, in fact, the energy budget for operating the building. Also in the United States, once you move away from that new construction market and get into the retrofit market, energy modeling is again used as a predictor of energy budgets. And it's usually energy savings. So some of us are familiar with things like energy service companies, or ESCOs, and their projects where the project team puts up its own money or investor money and guarantees energy savings against that money. And they use energy models, but they tend to, they call them part of an investment grade audit. And on the owner side, we really like that term, investment grade, the idea of an investment grade energy model. So what is the difference then between a U.S. new construction compliance model and an investment grade energy prediction? And the answer is risk adjustment. Now what would be really great would be if somebody had already developed a standard for this, right? We got some feedback that says we really need an ASHRAE standard for how to do that, which would be cool. It would be great if we could find a standard that was actually called something like evaluating operational energy performance of buildings at the design stage. Here it is. Evaluating operating performance of buildings at the design stage. Wow, amazing. Thanks, by the way, to, we had some consulting groups that were giving us feedback on our white paper that turned us on to this and other references. There's not just one source here. There's a couple of different references you can look at. The EPA has it as part of their Energy Star program, this thing called the Statement of Energy Design Intent. I like it when you can find multiple sources about how to do something. The good news for these is that they all talk about some of the same things. They basically talk about running sensitivity studies for some very basic things, right? Operating hours, occupancy, weather, variances in lighting energy, HVAC energy, plug loads, accounting for things like elevators and escalators. For some reason, the British standard spends a lot of time on elevators and escalators. But these are some very simple sort of sources of error in design models. The good news is that there's not 100 sources of error in design models, right? There's just this list right here. And when things go wrong between modeled energy and actual energy, they go wrong in one of these buckets. So I did mention that we did a calibrated energy model at the end of a year on that Antelope Valley project, which I'm flashing on the screen now, but don't try to read these numbers. I'm going to talk more about this quite a bit later. So as we are doing life cycle cost assessments on our project, what we're really talking about doing is trying to add a little more of that reality in, or to start thinking in terms of risk. If there's one thing that I've learned in the last 3 years, it is this. The margin of error on energy models is not zero, and we need to face that, and we need to face that squarely. We can't pretend that energy models are accurate to a decimal point. The best case scenario we've seen is when we have 2 years worth of real data on an existing building and we do a calibrated energy model, and in that case the error is somewhere in the neighborhood of 10 to 15%. If we took the energy modeling that we've seen to date and compared it to the actual use, On new buildings, the error is more like 50%. So what we're saying at this point is that unless we have a pretty compelling reason to talk about a lesser error, we probably should be looking at 10 to 15%, more realistically 20% error in the energy models. Now, the graphic that you see here comes from a conversation I had with one of our engineers who talked about diminishing risk as the project matures. This part makes sense to me. I don't know how that would actually play out in numbers, but, and so those numbers are just made up to illustrate the point, that by the time you get into construction documents and produce a model that's ready for measurement and verification, you should actually know your envelope pretty well. You should know your zoning. You should know your operating hours, your boiler temperatures, pressures on pumps, those kinds of things. You wouldn't know those in schematic design. By the time you get up to construction documents, you would know those. We are going to talk about measurement and verification in a little bit, but one of the points that's important to understand here is that when we are making early design decisions, and that is when we make those financial decisions on the projects, that is when we need to carrying the most risk, right? That's when our energy models have the most risk, and we need to think about them as the most risky. So what does that look like? And I'll be honest, we haven't seen projects that actually accommodate for this risk. And so let's take a look at what that would look like. So I'm going to show this hypothetical illustration, right? And I did steal this from a project, so my apologies for that. But what you're looking at here is 7 different HVAC systems proposed on a project, and the y-axis here is EUI points, and then the x-axis is all the different options for the projects. Now, one way to think about this is that you could round the results to the level of significance. If we assume the error in these numbers is 20%, then the average of all these scenarios is about 60 EUI. 20% of that is 12. And so we would round each one of these numbers to the nearest 12, and we would wind up with something that looks, well, that looks like this. And that simplifies things, actually. Out of those 7 different systems, what you're now looking about is you're talking about 3 levels of energy. You have your baseline energy, you have better energy, and then you have best. And for financial reasons, during schematic design, I think this is really the right way to look at things. This is the way to look at things within the case of the error of the project. Now, I'll be the mean, nasty owner here and go ahead and say that when it comes to energy costs, the difference between the base case and the best option here is only about 50 cents a square foot. And so if you're looking for a 5-year payback, that's only about $2.50 a square foot, right? So if your base case is $45 a square foot first cost, there's absolutely nothing here that would ever justify an additional $5 a square foot of spending on your project. But it's actually worse than that, because Kaiser has a cost of capital, which is 11%. And yes, we've had feedback on that from the design community. And yes, we're working on that number internally. We may get to see movement in that number, but there is a number. We're not a government agency where our cost of capital is 0 or 2%. We're not a for-profit corporation where our minimum return is 20%, but we do have a number, and right now our number is 11%. So if you look at this difference on capital with a cost of capital and a 5-year payback, it really just does not justify any additional spending within the first budget of your project, right? So, this is actually the calculation that would show you that, right? We do have a cost of capital, so the net present value difference between those 2 options is quite slim. So, now in talking about that, I've had some pushback. I had one engineer tell me that this is unfair. He said, if I have an energy model that shows 5% better, if option 1 shows 5% better than the baseline, hey, that's legitimately 5% better. All the elements that introduce error into the energy model introduce error into all the options, and so an option that is 5% better than the base case is still 5% better once you add in all those errors. And that is true, but you have to kind of think about that for a second. It's a very weird thing to think about, and so I'll try to use this chart to explain it. If I have a model that says that my building EUI is 100, and I say that that model has 20% error in it, then the real performance of the building should be somewhere between 100 and 120. Now, I have no idea what distribution that error is, so assume that it's random. If I were to build a whole slate of those buildings and they all modeled at 100, then all the results would land somewhere in the range between 100 and 120. Now, if my model for option 1 says that it's, 80, and I add 20% to that, that gets me to 100, and that scenario is actually very easy because I beat the error. So all the possible outcomes of option 1 are better than all the possible outcomes of the base case, if that makes sense. Those are the top 2 bars in this chart. But if my model for option number 1 says 95, that's only 5% better, and so the error ranges overlap. Some of the possible outcomes from option 1 are the same as the possible outcomes of the base case, and only 20% of the outcomes of option 1 are actually better than the base case. So this becomes kind of a risk-adjusted scenario. You could think about this in terms of betting. You're getting odds. There's a 1 in 5 chance that option 1 will save energy relative to the base case. So if you were going to put money on this, you're taking a risk, and you'd want to get those odds back. You could invest money on option number 1, but you only want to bet $1 for a $5 return. I know it's a weird concept to think about, but that's really how we have to start living with error in our models, which we really haven't done yet. Well, to wrap up on risk, hopefully, I'm going to go back to this slide just to show it. Hopefully, you can use this concept to do less work, right? We've seen some engineering teams that run 30 or 50 scenarios in their life cycle cost studies, and that's great. We always encourage that. But we have had teams that complain, well, it's too much work, it's busy work, it's not valuable, and I agree with that also. If you run a few energy scenarios and nothing produces more than a 5% difference, then I would say there's no need to do a whole bunch more work on that. You don't need to do cost estimates. You don't need to do operating cost estimates. Those don't matter, right? I felt kind of bad a couple weeks ago. We had an energy guy in here, and he showed us a project where he had done 10 or 11 HVAC options on a project, and he had costs, he had descriptions, he had outline specs, he had sketches, and all of the models were within 5% of each other, and so we took one look at it and said, well, use the one that's lowest cost. And it was a bummer because clearly this was an engineer who stayed up all night, putting these scenarios together. So I felt legitimately bad, but that's, I think we can simplify the effort that we're doing during life cycle cost by accepting the risk and only looking at things that really move the needle across the threshold of that risk. On the other hand, if you have 5 options together and none of them create any difference on the 20% risk, then you might want to spend your time brainstorming more options and try to find, things that actually do get outside the limits. Okay. So this is the time to talk about baselines, which is confusing business, and I think just about all the projects that we've gone through energy models have struggled understanding baselines because you can have a million baselines. If you're in California, there's Title 24 baseline. For LEED, you have an ASHRAE 90.1 baseline. The 90.1 baseline could be 2007, or it could be 2010 or 2013. They're all different. Earlier, on the Antelope Valley business case, I showed you that sometimes we use a Kaiser baseline, which is based on the average utility spend in similar facilities in the same region. There are also Energy Star baselines. You can go on and on and on and on. So in the Kaiser project world, the baseline option is the lowest first cost option that meets the project requirement, and the key phrase there is that meets the project requirement. We had a project a couple of weeks ago that was talking about doing a constant volume HVAC system in an operating room floor. They said, hey, we could save a whole bunch of money if we just eliminate all the air controls on the OR system and just run it all the time. And that's true. You could save a bunch of money. But those OR controls are a project requirement. They're required by our KP design criteria, so you can't meet them, and your baseline is not the system that eliminates them, because that's a system that does not meet the project requirements. Likewise, you cannot skip LEED certification. You can't skip the EUI targets. Those are KP project requirements. And so the baseline option is not the lowest first cost option. The baseline option is the lowest first cost option that meets the project requirements. So let's kind of move to the fun part, which is measurement and verification. What we really want to do with our energy models is we want to produce a set of month-by-month, end-use-by-end-use predictions that we can use to validate the performance of the building as it starts working. This is that same project that I've been talking to you about, the Antelope Valley. Like I said, we did calibrate an energy model at the end of the project, but this is the dashboard that we actually used for the project. And what you can see is that every month we have a prediction for how much energy, that's the one in gray, the prediction for how much energy that building is supposed to be using, and then the actual energy is coming in with the green. So you can tell relatively quickly within a month or within 3 months whether this thing is on or whether this thing is, you know, off by an order of magnitude. And by the way, the predictions that we're looking for are broken down into those end uses, interior lighting, exterior lighting, to the level that you're metered is the level that that you should have, right? So, and the funny story about the dashboards is about 3 years ago, I had a consultant in my office, and we were talking about these energy dashboards, and he said to me, he goes, hey, anytime you do a dashboard, it takes a year to get it up and running. And I kind of laughed. I said, no, it can't be that hard. You know, we have really good project teams. We'll get this done. And so far, we actually have 2 of these energy dashboards that are up and started, and in both cases, at least 6 months and closer to a year to see a set of numbers that legitimately reports what's going on in the building. We are very much hoping that that gets better. We have a slew of projects in construction right now, and they have dashboards coming up, and we're going to be pushing hard during commissioning so we can try to avoid this dashboard startup problems in the buildings where the GC's already packed its bags and moved on. So stay tuned for more on that. But the M&V starting point is really important. We need the energy models to state how much energy should be used month by month in whatever buckets make sense for the project. And really what we kind of need is a fail criteria at each bucket, like the lighting energy bucket. We'd like to know when should we throw up the red flag, what defines successful performance, and the metering and energy dashboard needs to align to support analyzing that. We'd like to, on the projects that we're rolling out right now, we'd like to be able to tell within the first 2 months of lighting energy data to see if that building is doing okay or to see if that building is out of whack. That way we can do something about it. We can actually kind of look at what some of those problems would be. And so on Antelope Valley, we did this calibrated energy modeling at the end of the project. We have this, by the way, in white paper form. It is also in for publication by ASHRAE. It will be presented at the January conference. So this is public data as far as I'm concerned. And this is just one building story. We've had a lot of designers tell us that weather can shift performance by huge margins and that weather and occupancy, in this case, weren't that big of a deal. In this case, there are 3 big stories. We had the sort of equipment efficiency, the zone airflow, we had some lighting. The lighting is a positive story. The performance is better than what was modeled, but that also makes the areas with worse performance that much worse. One of those, the zone airflows, is something that could be addressed with better coordination between the designers and the energy modelers. The biggest story here was the mechanical equipment efficiency. In order to calibrate the model, our guy had to derate the HVAC equipment by a significant margin, and the worst was the boiler. Even after derating the boiler, you see this huge bucket here, 17% bucket that is called unaccounted for natural gas that we literally can't explain. And the only thing that uses gas in the building is the boiler. So like the crappiest boiler system on the planet shouldn't be using that much gas. And I know if you're a mechanical engineer on the phone that you want to call us and tell us all your little pet theories about why you think that natural gas is going, but trust me, we looked at them all. Guys looked at a lot of them, and we cannot explain that natural gas yet. So we still have some things that we could do, like ripping apart the whole boiler system and reassembling the controls, but that's probably not where we're going to go with that. Wouldn't be worth it to do so. So I do want to be clear that as we move forward with energy modeling, this is not a matter of Kaiser Permanente looking to the design community, holding you liable for the difference between your model and actual performance and then suing you for the difference. That's not what this is. We're not saying that. I know that the GSA has moved into some projects where there's some performance incentives. We may move into a performance incentive type scenario in a few years, but we're not there yet. And we're fully aware that there isn't a design firm in the nation that has any real experience in accurately predicting energy consumption of buildings, at least not that we're aware of. And another important note is that we understand the variances between the modeled world and the real world have to do with the way that the building is operated. If the facility operator disables all the sequences and runs it all in manual, then all bets of energy performance are off. Of course, that touches into a whole other topic of the building where buildings have to be designed to be easily operated. That's a topic we'll eventually dive into, but it would keep us occupied for the rest of the day. What we have seen in some of the energy modeling efforts and the measurement and verifications that we've done so far is that some of the energy performance issues could be addressed. Some of the others were more inherent to the building and wouldn't be corrected without major capital investment. So we're not going to rip out brand new air handlers. We're not going to tear apart a brand new boiler system. So the energy model needs to realistically address energy consumption so that the issues that we see in the M&B program that show poor performance can be corrected. What we're really learning to do is learn with our partners, our preferred provider network. We have a network of providers, and we want to be working in partnership with them. We all sort of need how to do this together. I'm giving this presentation, but if you think I'm talking from authority or experience or that I know how this is done from my years of doing it, then think again. I've never done it, neither of you, we all understand that, but we want to know what we're talking about. And in this hour, we also know that what Kaiser is asking for is different than what your other clients are asking for, and we need to make that clear. My commitment to the design community personally, I think Kaiser's commitment to the design community, is to try to give the feedback and make this kind of data very accessible. If you want the energy data on a project that you've designed for us, just ask. We'll give it to you. We're committed to pushing that stuff out to the industry. We'll post our white papers to InfoZone. We've submitted studies, and we'll post them through ASHRAE. I think the design community needs feedback and data to learn from, and in my role, I'm pretty committed to getting that to you. So that being said, hopefully, it's 1:30, so we've got ample time for Q&A. I'm going to ask Malini, these are the names of the folks on our project team. I'll ask Malini if we've had questions through WebEx. And
not yet. Not yet.
Excellent. Which means everything that was said was clear and perfect and succinct. So you can either type questions into the WebEx chat box, or there's also the raise your hand option in WebEx if you're familiar with how to use the raise your hand option. Yes?
Is there any example of what that, your last slide when it talks about, your model should have those targets predicted, do you have any example of what that shows up like?
What that physically looks like on and that is where kind of the M&V template that we have on InfoZone has a blank matrix in there that is what we're looking for. But we're active. I'll say that we're actively working with the design community to come up with that, because I think it does need to be both. It's like within each bucket, lighting energy as an example, you should have a January, February, March, April, May, June, July predicted energy consumption for lighting, and then in my mind, there's got to be some sort of fail criteria or upper limit point that says, this is where we want to throw up the alarm bells, right?
Yeah. Okay. Thank you.
Okay, I've got a couple questions coming in. When will this be posted for review? And I don't actually know, but think these go up relatively quickly. I'll commit Melanie and say that these are there for, this will be up in a week or two? Yeah?
Perhaps, yeah. Yeah.
Okay.
There's some more questions.
Another question, why would we want to develop an energy strategy for new buildings that have not yet completed scoping? We have no idea what the staffing might be. That's a good question. On the new building side, the biggest variables are 24/7 occupancy versus weekday occupancy, and whether or not it's a B occupancy building or an I occupancy building. And so there is there are some tranches that you can slide the buildings into almost immediately at the programmatic stage, and then but those are risk. As you develop sort of the building into its program, then you're going to be able to narrow down on that number more. Some of the stuff that I've seen, we had some consultants that sent us some other M&V studies while we're doing the white paper, and I've been surprised to see how little the occupant density of the building actually matters to its energy consumption. That's something I've long thought, the difference between 10 people in a building and 20 people in a building should mean the world. But from what I've seen so far, that in reality may be just kind of a marginal factor. This webinar, by the way, is recorded, and so so you will be able to catch up with it later if you'd like to do so.
There are no more questions.
Excellent. So what you've got up on the board are the email addresses. This is my team. So hopefully at least one or two guys up on that team. I see some hands raised on the chat.
Yeah, we could talk to Chris. Chris, you can raise your voice.
Hello?
Yes, we can hear you.
Hi. So I think that this whole presentation seems to be pretty similar to what I've been recently doing with the monitoring-based commissioning plan. So I wonder what's gonna be the difference, like if you figure that your measured data is different from your predicted data, are you gonna adjust your energy model, or are you going to adjust your operation?
In each case, I think there's going to be, to speak to on the new construction side, there's a little bit of difference between the continuous commissioning and the new construction side. But continuous commissioning in existing building side, you kind of have some baseline data to start with. Which means by itself that should lend you to a little bit better ability to predict. But then in any sort of measurement and verification scheme, you're going to get variances that come in, and you'll need to determine if those variances are based on operations or utilization of the building, or whether they are, system deficiencies. And I think you have to make decisions on those as they come in. If the building's being used in a way that doesn't necessarily match the design intent, but it is the way that Kaiser wants to do business, then we would adjust the model and essentially recalibrate the baseline of our expectation. If it's on the other hand running in a way that we did anticipate, and there's some aspect of the system that's not performing, then we would be more likely to go after that.
Okay. And one other question is that I saw that you have like 10% error, 15% error, and even 50% error. So do we just have a standard to say what's going to be the error that beyond which that we have to recalibrate our model? And does that, for example, if there's a 10% error, does it apply to both demand and consumption and electricity and gas?
That's a great question. We do not have a standard error, and I didn't, in kind of thinking about this and trying to put it together, I haven't been able to find anywhere that kind of a standard error for energy modeling is given. The 10 to 15% number, by the way, just comes from our experience when we hire consultants to do calibrated energy modeling, and I see that at least one of them is on this phone call. We generally calibrate an energy model to 2 years worth of bills or 3 years worth of bills, and we'll get those within 10 or 15%. I consider that to be a best case scenario. On the new construction side, we have seen projects where the predicted energy use and the actual energy use are off by as much as, a factor of 3. And so I think on new construction, to assume 20%, that's kind of a number that we're picking right now, but I couldn't give you a citation for that if you asked me to.
Okay, is that going to be a monthly error or a yearly error?
That would be, I would see that as an annual number error, because that's generally the result that we're looking for out of the model. But frankly, I'd be completely open to talking to the energy modeler and the design team about what they think the monthly, the error in the monthly numbers, appropriate error in the monthly numbers is, and where the alarm point should be.
Okay.
So the short version of that answer is I don't know.
So, excuse me. So I used to work on LADWP projects for energy auditing, and they do have a guideline that they ask the both demand and the consumption of electricity and the gas to be within 10% monthly. So we did try to accomplish that, and it seems to not very hard to obtain. So I think that will be a good start.
Yeah. Okay. I would like to see that, by the way, if there's a.
Okay. I can send you their guideline. I can send to Travis.
Yeah, that'd be great. We did also see we benchmark a little bit with the University of California and their standards group, and they have some what they're rolling out that's called a benchmarking. I don't know. It's like a benchmarking based prediction that they're using for new construction projects. Okay. And they talk about a 10% margin within that. Mm. I see Kevin Long has a hand up. Can you unmute him maybe, or?
Actually, we have first Kumar Maslumian.
Okay, Kumar.
Yeah.
Kumar, you're on Car Talk. I don't see that he has a phone, Malini. Maybe he's not.
All right. So then next is actually Rick.
Rick.
I just had some questions, but I texted them to you. But basically, can you talk a little about maybe of all the energy technologies out there that we've talked about, what do you see as the most exciting and promising technology of the future that we should really be watching?
On the new construction side, or?
Well, on new construction and also on commissioning.
Well, I don't know. You know me, I get excited about different things on different days. The one that I'm seeing today is that we have had a struggle, and just to share with everyone on the phone, we've had a real struggle with trying to leverage commissioning as a professional service effectively into our portfolio, get the results that we want, while sort of ensuring the quality. I like to say that I can show you the last 5 buildings with 1,000-page commissioning reports, and yet they still have sort of fundamental building energy usage discrepancies. And so the 2 things that I think are ripe for innovation, one is just commissioning as a service has always been done, at least for the past 10 or 15 years, according to these playbooks that are written by ASHRAE or that you find USGBC has them over the years. And we've heard about a couple of folks that are innovating the commissioning process itself, you know, walking away from some of those playbooks and coming up with algorithm-based or computer-based, more in line with continuous commissioning. I think that's tremendously exciting to start commissioning projects with layover software and things like that. And then I also think the building controls and just the user interface of building controls and the code quality in building controls are a tremendous opportunity for the industry right now. And we're seeing some innovation in small corners of the marketplace around that I think make a huge difference.
Okay, Kevin Long.
Kevin.
Travis, how are you doing?
I'm pretty good, sir. How are you?
Good, good. Hey, I like the presentation. Very well done. So I just wanted to, and I'm sure it's all built in, but I just wanted to clarify, as far as your energy models, I'm assuming they take into consideration life cycle equipment cost and maintenance cost and all of those additional things that are impacted by each different scenario that's out there as far as a design solution.
Yeah, that's a great. I mean, that's a great point, and it's also a great rabbit hole. I almost view, contrary to what you just heard in the last half hour, where I said that energy models are chock full of error. I almost view the energy model as the least erroneous part of a life cycle cost assessment, because we've had a very, very difficult time nailing down predictive operating costs or O&M, you know, repair and maintenance costs. We have some internal numbers within Kaiser that we try to use to track that. We have some external sources that we've tried to benchmark that against, and it's been amazingly difficult. And so what we've told our design teams at this point is that unless you have a damn good reason to say that your operating cost is going to be fundamentally different than the baseline system, then just don't even use that as a variable. And the same holds, unfortunately, for service life of equipment. There's some standard tables out there for service life of equipment, but as you well know, Kevin, a lot of what we deal with in NFS is the 20-year boiler that we're replacing in 5 years, or the 25-year-old package unit that we still have in a building at year 30. And so that is also kind of wildly unpredictable. So contrary to my skepticism on energy modeling, I do actually think that that's the most consistent chunk of the life cycle cost equation until we can nail down data on the other pieces. Please disagree, though.
No, I absolutely agree. It's I agree wholeheartedly that the hardest part to predict is operations and how and when things are going to be controlled, how they're going to be controlled, and when they're going to break.
Well, you and I will figure that out and make $1 million in our spare time.
I'm looking forward to that. That was all I had, though. Thank you, though.
Okay.
That's it. No more questions.
All right. Well, excellent. That took us out to 10 till. We did an hour WebEx in 50 minutes. If you're on the East Coast, thanks for sticking with us. And we will close up shop. Thanks, everyone.